This is problem 3 on page 41. Determine the net force on the 10 microcoulomb charge. So they give us all the 4 charges and the distances between the 10 microcoulomb and the rest of them. So so approach a problem like this, right? You're trying to find like, hey, what is like, you're trying to basically you're summing up the forces by this charge and this charge and this charge, right? And they're vectors, so you can't just, right? So we think about the electric force equation, Fe equals K Q1, and I'll talk about the absolute values, Q2 over R squared. You can't simply just be like, okay, let me plug these two in the distance, boom, add that to these two, plug it in, boom, and then add finally the force between these two. You can't just add up 3 forces because they're all in different directions, right? Or at least some of them. Some of them are vertical forces, some of them are horizontal forces. Net force is a vector. That's asking magnitude and direction, right? It doesn't say determine the magnitude, it's just saying determine the net force. That means both magnitude and direction. So what we have to do is we have to kind of, first of all, to understand the problem, draw an FBD, right? Let's say this is my FBD of the 10, here I'll do it here, of the 10 microcoulomb charge. And I'm going to also label these charges, so I'll say 1, 2, and 3. So there's going to be the force by this charge. Which direction is it going to be? Well, they're both positive, they're going to have a repulsive force. That means this thing is going to want to go away from this positive. So that force is going to be, I don't know my rights and lefts, to the right. So I'll say F1. Okay. F2. What is the direction of that force? Well, it's going to be, you're going to guess, probably vertical, right? Because it's in the vertical axis. It's going to be upwards, right? Because this is a positive, this is a negative. This thing wants to get closer to the negative. There's going to be an attractive force upwards. So I'm going to say F2. And then finally, the force between these two, opposite signs, they're going to want to attract. This thing is want to get closer towards the negative 40. So I can see that, I can see kind of the direction of the forces now and how I can approach this problem. I know for sure I'm going to need to find the F net in the x direction and the F net in the y direction. So the way I'd go about doing that is I would say, okay, the F net in the x direction, right? My horizontal, x just means horizontal, like because of an xy axis. All my horizontal forces are F1 and F3. They're in the same direction, so I'm going to add them. So it's going to be F1 plus F3. Now, I can plug in like my electric force equation. That's why I added the absolute values, because the negative charge, like if I do a positive negative, sure, my force is going to be negative, but that like I'm deciding my direction. I'm deciding this way is positive, so they're both positive forces because they're both pointing to the right. The negative actually just means that it's an attractive force. That's why sometimes the FG equation, you might see it with the negative. The negative just means an attractive force. So don't worry about that though. That's just like why negatives appear and stuff. So F1, K, write your equation. K, Q for 10 microcoulomb, I'm using big Q, times Q1, there should be absolute values, over R squared plus K, Q times Q3. So R1 squared over R3 squared. So this is like R1, R2, R3. And then from here, you just want to plug in your numbers. So K, I'm not going to plug that in, 9 times 10 to the 9th. Make sure to do that on your calculator. 10 times 10 to the negative 6 coulombs times, this is charge 1, so 15 times 10 to the negative 6 coulombs over R1 squared, which is 3 meters. So I'm literally just using the diagram, and then I'm just plugging in, like, this distance, they're 3 meters away. I got to put that into my equation. Now when I'm dealing with this charge, right, the F3, I want to do all of the distance between these two charges and the size of these two charges. So it's going to be the same thing, K 10 times 10 to the negative 6 coulombs times, running out of space here, 40 times 10 to the negative 6 coulombs. Pretend that's going over there, all over 2 meters squared. You could plug it in. I got, what did I get? I got 1.05 newtons. That might be wrong. I don't know. I plugged it into my calculator. Could have been a calculator mistake, but I'm very confident that this is how you would set it. Like, this is how you want to plug it into your calculator. So, cool. I have the x direction. Now I got to find the y direction. So F net y. I'll do this. This one's really simple, right? There's just one, like there's only one y direction force. It's the F2, and I'm gonna say positive y is upwards. So positive force. You could technically, if you really wanted to, say positive is downwards. To me, that makes no sense because we don't have any downward forces. But it's in your hands. You can decide. I'm just gonna make upwards positive. So F net y is gonna equal K Q. Big Q for central charge, Q2 over R2 squared. And then I'm going to plug in my numbers. K, it's going to lean down here. Q is 10 times 10 to the negative 6. And yeah, that's why I'm not adding my negatives, right? You might have noticed 40, it's negative 40, but I'm taking the absolute value. So 25 times 10 to the negative 6 over 5 meters squared. You can imagine this is probably going to be a really small force. I got 0.09 newtons for my F net y. Now, you might be saying, wait, why are we doing all of this like F net x, F net y, right? Why can't, now can I just add these two? Like is that what's going to happen? Well, if you look at your vectors, and I have a whole video on vectors, if you need some review, if we draw back our FBD, we're going to have an F net 1 here. Now, we're also going to have an F net 2, right? Or so I should say F1 and F3, right? Not F net 1. We're going to have F1 and F3. I'm going to draw that as one big arrow to kind of represent my total horizontal force. So I should do this. So my Fx, my F net x, and then I have my F net y, which is upwards. And if you remember how to add vectors, we do tip to tail. So I take the y and I put the tail on the tip of x. So I draw it kind of like up. And what you're going to notice is when I do that, I get a right triangle. And I can draw a hypotenuse. This hypotenuse is the total F net. So if I want to find the size of that F net, I got to use Pythagorean theorem. So I can say we're going to have an F net squared is equal to F net x squared plus F net y squared. Alright, so I know these two values. They're 1.05 newtons plus 0.09 newtons. And you can probably imagine this is a really small number. It might not make much of a difference. And then I have F net squared. So I'm gonna actually just take the square root of both sides, right? To get rid of that squared. You should get F net, or at least the magnitude of F net, is equal to 1.054 newtons. This number kind of makes sense because, hey, you have these two charges that are a lot closer, right? 2 meters, 3 meters, compared to the up top charges, 5 meters. So they're going to have stronger forces, and they're both pushing this way. So there's a big force this way, not as much of a force upwards, so the total F net is going to be pretty similar to what this is, just with that little extra nudge by the upward force. So I'm not done yet. I got to figure out the direction. And the way I do direction, right, because there's no up, down, right, like, it doesn't really work. To do direction, I can use an angle. So this angle right here is kind of the angle above the horizontal that I can use to find the direction. So if I want to find that angle, I can use my calculator and do some inverse trig. So theta is going to equal tan inverse. So my opposite is F net y, which we found was 0.09 newtons, over my adjacent, which is 1.05. I don't know why I blanked. And when you do that, you get a theta of 4.9 degrees, yeah. I'm just looking at my work. So it's going to be, so my final answer, I would say F net is equal to 1.054 newtons at an angle 4.9 degrees above horizontal, right? Because I found it like above the horizontal. And this number, once again, makes kind of sense because it's like your force is not going to really be angled up that much because this charge creating kind of a weak force on the 10 microcoulomb. So yeah, hopefully this makes sense. I'm just gonna finish it like that. Let me know if you have questions. Let Mr. Gustin, and that's why I didn't go over 1 and 2 because Mr. Gustin did that. But thank you for watching.